Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you could just step outside tonight, like far away from the city lights, and look up at a perfectly clear, moonless sky.
You'd see what humanity has been staring at for, well, tens of thousands of years, right?
Exactly. Just this vast, dark canvas, dusted with familiar, twinkling pinpricks of visible starlight. It feels so timeless. And really, it feels quiet.
Yeah, quiet is the perfect word for how we perceive it.
But I want you to imagine if you could somehow, flip a switch right in your visual cortex.
Yeah.
Suddenly, you weren't just seeing that tiny, narrow band of visible light that our human eyes evolved to process.
Right, because visible light is just a fraction of what's actually out there.
Exactly. So imagine you suddenly possess this completely different kind of vision, a highly tuned, specialized radio vision.
Oh, the sky you thought you knew would just completely vanish. I mean, those quiet, twinkling little stars.
Yeah.
They'd fade entirely into the background noise. You wouldn't even notice them.
That's wild, because the darkness would suddenly be dominated by these colossal, glowing, ethereal structures.
Oh, absolutely.
And we aren't talking about little smudges of light here. We are talking about monolithic, brilliantly glowing shapes just hanging out there in the void. Massive, distinct X and Z formations.
And the scale is just, well, it's hard to wrap your head around.
It really is.
Yeah.
These things are so unimaginably huge that they completely dwarf the entire host galaxies that gave birth to them.
Yeah.
I mean, we are talking about structures that span hundreds of thousands, sometimes millions of light years across the universe.
Millions of light years.
It is this completely hidden, monumental architecture that we are only, just now beginning to truly comprehend.
And that hidden architecture is precisely what we're going to get into today, because we are looking at a truly groundbreaking shift in astronomy right now.
A huge shift. The identification of over 1,000 new so-called winged radio galaxies.
Right. And for decades, these objects were considered bizarre cosmic rarities, like a glitch in the matrix, so to speak.
Just weird anomalies.
Exactly. We only had a tiny handful of them cataloged. But this massive new haul of data fundamentally rewrites that entire narrative.
We're moving from looking at a few strange freaks of nature to studying a robust, statistically significant population.
Yeah, and this isn't just about, cataloging giant letters painted across the sky for the fun of it.
Right. There are real stakes here.
Absolutely. This discovery strikes at the very heart of how we understand the life cycles of galaxies themselves. It shows us that supermassive black holes are not just these cosmic vacuum cleaners passively sitting in the dark and swallowing matter.
They're doing way more than just eating.
Oh, they are hyperactive sculptors. They're literally reshaping the universe around them over timescales of tens to hundreds of millions of years.
Okay, let's unpack this, because the sheer scale of these phenomena is it's mind-bending.
It really is.
When you say a structure is 1 million light years across, light is the fastest thing in the universe. It travels at 186,000 miles every single second.
The absolute speed limit.
Right. And it still takes 1 million years just to get from one side of this X to the other. It's almost terrifyingly large.
It's definitely humbling.
But before we can really appreciate why these X and Z-shaped winged galaxies are so weird and wonderful, we really need to establish a baseline. We need to understand what a quote-unquote normal radio galaxy is supposed to look like.
You can't understand the exception until you understand the rule.
Exactly. So what is the standard model here?
Well, at the very heart of a standard radio galaxy, you have the engine. And that is an active, supermassive black hole.
And when astronomers say supermassive, they really mean it.
Oh, yeah. They mean an object with a mass of millions, sometimes billions of times that of our own sun.
Billions.
Billions. And all of that mass is crushed down into a surprisingly compact volume. Now, as this black hole gravitationally pulls in surrounding gas, dust, and, sometimes unlucky stars.
Right, getting a little too close.
Exactly. That material doesn't just fall straight in like a rock dropping off a cliff. Because everything in space has some residual spin or angular momentum, so the material spirals inward.
Like water swirling down a drain.
You're on the right track, but we need to factor in the sheer violence of this environment. It isn't just hot water.
Fair enough. Superheated water.
More like a swirling, incredibly dense, and unimaginably hot disk called an accretion disk. The friction between the particles in that disk, combined with the immense gravitational crushing force, generates so much heat that the gas turns into a plasma.
So the electrons get stripped away.
Violently stripped away from their atomic nuclei. And because plasma is a soup of charged particles, its movement generates these staggeringly powerful, twisting magnetic fields.
Okay, I'm picturing this swirling, glowing tornado of magnetic fields.
That's a good visual. Now, here's the crucial part. Not all the matter falls past the event horizon, the point of no return.
Some of it escapes.
Yeah, a fraction of that intensely hot plasma gets caught up in these towering, twisting magnetic fields that form near the black hole's poles. And these magnetic fields act almost like a cosmic particle accelerator.
Like the Large Hadron Collider, but naturally occurring.
Exactly, but on a galactic scale. They tightly wrap and constrict the plasma and then violently launch it outward into space at velocities approaching the speed of light.
So the black hole is effectively a cannon shooting this plasma out.
Yes, and it shoots it in two opposite directions, straight up and straight down from its poles. We call these bipolar relativistic jets.
Bipolar relativistic jets, got it.
Punch right out of the galactic center, tearing through the galaxy's interstellar gas, and break out into the vast empty space between galaxies, the intergalactic medium.
Wait, let me stop you there. You just said it breaks out into the empty space between galaxies, but then you say the jets eventually slow down and form giant clouds.
All right.
How does a jet of plasma moving near the speed of light slow down and splash if it's traveling through a complete vacuum? There's no friction, right?
That is a very common misconception. The space between galaxies is not a perfect vacuum.
It's not.
No, it is incredibly sparse, maybe only a few atoms per cubic meter. But when you have a jet of plasma millions of light years long, traveling at 99% the speed of light, those few atoms really add up.
Like bug splats on a windshield going 1,000,000 miles an hour.
Exactly. The intergalactic medium, or IGM, possesses enough density to eventually act like a brick wall to these jets.
A really, really diffuse brick wall.
Right. And as the incredibly fast, tight jets of plasma ram into this thin gas over hundreds of thousands of light years, they experience a terminal shock.
Terminal shock. That sounds intense.
It is. It's a massive shock wave akin to a continuous sonic boom. The forward momentum is halted and the plasma billows backward and expands outward into giant glowing clouds.
And those clouds are the lobes?
Yes. Astronomers call these massive clouds radiolobes.
Okay, that makes total sense. So if I am trying to visualize this standard radio galaxy, I should picture two cosmic fire hoses strapped back to back.
Back-to-back fire hoses. I like that.
Shooting highly pressurized water well, plasma in completely opposite straight lines. And where the stream hits that invisible wall of the intergalactic medium, it splashes and pools into these huge, bright puddles.
The puddles being the lobes, yes.
So the standard shape is basically a straight line with two big blobs on either end, like a linear dumbbell shape.
The standard morphology is strictly linear. You have the bright central core, the two thin, incredibly fast jets, and the two massive, billowing lobes on the ends. That is exactly what astronomers expect to see.
Okay, so if that straight line double fire hose setup is the normal behavior, what exactly goes wrong to create a wing?
That is the million-dollar question driving this entire field of research right now.
Because we're trying to figure out how we get from a straight line to these massive X or Z shapes.
Right. So when astronomers look at these winged galaxies, they still see those two primary bright lobes, but they also see these vast additional structures.
With wings.
Yeah, extensions of plasma that jut out at strange perpendicular angles from the main axis. We call them wings. And what is vital to grasp here is that these wings are fundamentally different in character from the primary lobes.
How so? Different material.
Same material, different state. They are composed of highly diffuse, low-surface brightness plasma.
Meaning they are incredibly faint and hard to spot.
Exactly. If the primary jets and lobes are like a blazing focused spotlight, the wings are like a very dim, dying flashlight beam trying to penetrate a thick fog.
Oh, wow. So barely there at all.
Barely. They completely lack the bright, sharp shock fronts, the hot spots that the primary lobes have, where the jet is actively ramming into space.
So the wings are just kind of chilling out.
Yeah, the plasma in the wings seems older, more relaxed. It is lazily spreading out rather than actively punching forward.
And I imagine because they are so incredibly faint, they've historically been nearly impossible to detect against the background static of the universe.
Spot on. They just blend into the noise.
Which sets the stage for the big reveal. Now that we know what a normal galaxy looks like, and what a wing basically is, this faint ancient plasma extension, we need to dive into the specific shapes that have just been uncovered.
And the unprecedented volume of this new discovery is what really shifts the paradigm here.
Because we are dealing with two distinct structural flavors, right? The X-shaped radio galaxies, which the astronomy community calls XRGs.
Correct.
And the Z-shaped radio galaxies, or ZRGs. Let's break down the geometry of what observers are actually seeing in the data.
Sure. Let's start with the X-shaped ones, the XRGs. In these systems, the wings appear to emerge from very close to the galactic center.
Like right near the host galaxy and the black hole itself.
Yes, right from the core. And these faint wings shoot out at roughly right angles to the primary active jets.
Okay, so if your primary jets are firing north and south,
you suddenly have these massive, faint wings stretching east and west, intercepting right in the middle.
it creates a very distinct, highly symmetrical X across the sky.
It does. It's quite striking.
It sounds elegant, honestly. Two crossing swords of plasma. But the Z-shaped ones, the ZRGs, they don't follow that neat symmetry, do they?
No, they are decidedly asymmetrical. In a Z-shaped radio galaxy, the wings don't emerge from the central core at all.
Where do they come from then?
Well, the primary jets travel all the way out to the primary lobes, just like normal. But then from the outer, far edges of those main lobes, the plasma seems to sharply branch off or bend away.
Just veering off to the side.
Yeah, it produces this offset, twisted morphology. If you trace the path of the plasma from the tip of one wing down the main axis of the jets and out to the tip of the other wing, it literally draws a massive, sprawling letter Z in deep space.
It's just wild to think about these distinct letters stamped onto the cosmos. And what is staggering here is the sheer math of the discovery. I mean, to find these, astronomers didn't just casually look through an eyepiece on a Tuesday night.
Definitely not.
They scoured a monumental data set encompassing 4.3 million individual radio sources.
It's an ocean of data.
4.3 million. They had to sift through all of that, looking for incredibly faint, specific shapes.
And from that, they identified 1,024 candidate winged systems.
Which is a huge jump from the handful we knew about before.
Oh, absolutely. And after rigorously checking the data, to ensure they weren't just looking at artifacts or two unrelated galaxies overlapping by chance, they confirmed exactly 621 bona fide, absolutely certain winged radio galaxies.
Plus another 403 very strong candidates waiting to be conferred.
Exactly. And the breakdown of those confirmed sources is quite telling, actually.
How does it shake out between the X's and Z's?
They found 382 XRGs and 239 ZRGs.
Okay, let me do the math.
That gives us an X to Z ratio of about 1.6. So the highly symmetrical X shapes are noticeably more common in this particular sample than the twisted Z shapes.
I really want to emphasize the significance of these numbers for you listening, because prior to this, we had older surveys, like the VLA First Survey.
Right, which was a landmark survey in its own right.
A huge historic milestone in astronomy. But it only found a tiny handful of these winged objects. We are talking dozens, maybe.
Yeah, there were extreme rarities.
So to go from a few isolated oddities, where an astronomer could write an entire career-making paper just on one weird-looking galaxy,
Which they did.
right, to suddenly possessing a statistically robust catalog of over 600 confirmed sources. I mean, that completely changes the rules of the game. It alters the fundamental questions we can even ask.
What's fascinating here is how reaching a certain statistical threshold allows you to see hidden patterns.
Patterns that were totally invisible before.
Exactly. You simply cannot see demographic trends when you only have 10 or 20 objects to study. It's just noise.
Right, you need volume.
And because the team now has hundreds of these winged galaxies to analyze, the data clearly reveals something interesting. It shows that the Z-shaped galaxies, the ZRGs, tend to be systematically less radioluminous than the X-shaped XRGs.
Okay, let's make sure that's clear. Less radioluminous, meaning they just don't shine as brightly in the radio spectrum.
Right. They are outputting less overall energy.
So they're basically dimmer light bulbs.
Yes, the total amount of radio energy they emit into the universe is lower, and this is a massive clue.
How so?
Because these ZRGs are inherently dimmer, it perfectly explains why older, less sensitive surveys missed them entirely.
Oh, because they just couldn't see the dim ones.
Exactly. If you are sweeping the sky with an older telescope, only the absolute brightest, most luminous objects will cross your detection threshold.
Which were the few powerful XRGs we already knew about.
Spot on, that a vast population of fainter ZRGs was lurking just below our ability to see them.
Just hiding in the static.
Yep. So by finally having a survey sensitive enough to pick up these dimmer objects, it strongly suggests we are peeling back the curtain on a much broader, previously invisible population.
We aren't just looking at the brightest freaks of nature anymore.
No, we are finally seeing the average everyday population of winged galaxies.
Which immediately brings up the obvious question: how? How did astronomers suddenly find over 1,000 of these things when previous generations completely missed them?
That's the real story here.
Because it's not like these million-light-year-wide structures just popped into existence over the last decade. They have been hanging there the whole time,
Waiting to be seen.
The answer, it turns out, lies entirely in the specific kind of vision that was used to look at the sky. We need to talk about the telescope that made this possible.
Yes, we do.
Because frankly, it sounds more like a time machine than a traditional observatory.
It really is a remarkable piece of engineering. The instrument behind this massive haul is called LOFAR,
Which stands for?
the Low Frequency Array. Specifically, this discovery comes from the LOFAR 2-meter sky survey, data release 2.
Okay.
Now, LOFAR is not what comes to mind when you hear the word telescope.
Right. Most people picture a giant steerable dish. Like the old Arecibo Observatory in Puerto Rico, or those massive dishes you see in sci-fi movies.
Exactly. But LOFAR has no giant moving parts. None.
Wait, really? What does it look like?
It is a vast network of tens of thousands of relatively small, almost incredibly simple-looking dipole antennas.
So no big dish, just antennas.
Right. They look a bit like metallic spiders or wire racks staked into the ground.
That's so weird.
And they are spread out across fields all over Europe, with the central core situated in the Netherlands.
So how do a bunch of metal racks sitting in a field replace a massive satellite dish?
Through a process called interferometry.
Interferometry. Okay, break that down.
Instead of building one impossibly huge mirror or dish to collect faint light, which would be structurally impossible, astronomers build thousands of small antennas and link them all together.
Using, like, the internet.
Using high-speed fiber optics and incredibly powerful supercomputers, the computers precisely time when a specific radio wave hits each individual antenna down to the nanosecond.
Oh, wow. So they sync it all up perfectly.
Yes, and by combining all those signals mathematically, they create a virtual telescope that has the resolving power of a single dish hundreds of miles wide.
That is just brilliant. You cheat physics with math.
Exactly. But the hardware is only half the story. The really critical thing here is what LOFAR is actually listening to.
The frequency.
Right. It operates at 144 megahertz.
Okay, 144. To put that in perspective for everyone, if you get into your car and turn on the FM radio, you might tune into a station at 98.5 or 104.1 megahertz.
Right. The FM band.
So LOFAR is listening to the universe just a tiny bit further up the dial from your local pop music station.
It is. It is a very, very low frequency for astronomical observations.
So why does listening at such a low frequency act as the skeleton key for finding these specific winged galaxies? Why didn't high frequency work?
To understand that, we have to look at the physics of how this plasma glows in the first place.
Right.
The radio light we see from these jets and lobes is something called synchrotron emission.
Synchrotron emission, got it.
Remember those electrons in the plasma caught in the black hole's magnetic field?
The ones getting violently launched out in the jets.
Yes. As they travel out, they are spiraling around invisible magnetic field lines at close to the speed of light.
Sounds dizzying.
It is. And because they are moving so incredibly fast and constantly accelerating along these spiral paths, they emit radiation. They glow.
And that glow is the radio waves the antennas pick up on Earth.
Precisely. But here is the critical mechanism. The higher the energy of the electron, the faster it radiates its energy away.
It burns bright and fast.
Yes. And it emits that energy at higher radio frequencies. Conversely, lower energy electrons emit their radiation much more slowly and at much lower frequencies.
Okay, I think I'm tracking. So when a jet is newly launched and fresh from the black hole,
it is packed with highly energetic electrons glowing intensely at high frequencies.
Fresh jet equals high energy, high frequency. So older surveys were looking at high frequencies and seeing these fresh jets perfectly.
Yes, they saw the active jets beautifully. But consider what happens once that plasma gets dumped into the lobes or pushed out into the wings.
The central engine isn't actively accelerating it anymore, right?
Exactly. The plasma just sits there in deep space. And as it sits there over millions and millions of years, it ages.
It gets old and tired.
The highest energy electrons burn out first. They radiate all their energy away and simply stop glowing at those high frequencies.
They just go dark.
At those frequencies, yes. But the lower energy electrons, they take a lot longer to deplete their energy reserves.
They just keep simmering.
Exactly. They keep emitting a faint glow at the lower frequencies long after the high-frequency glow has completely faded to black. Astronomers call this a steep spectrum emission.
Steep spectrum, because the graph drops off.
Right. If you graph the brightness of the old plasma against the frequency, the curve gets incredibly steep. It is relatively bright at low frequencies, but drops off to absolutely zero at high frequencies.
Let me make sure I'm wrapping my head around this. Earlier surveys, the ones that missed all these galaxies, they were looking at higher frequencies.
And they were.
Which means they were basically blinding themselves to the older history of these galaxies.
That's a great way to put it.
It's like, imagine you were trying to track a wolf through a forest. A high-frequency survey is like using a specialized spotlight that only illuminates perfectly fresh, wet footprints.
Okay, I like this analogy.
You can see exactly where the wolf stepped 5 minutes ago, the active jets.
Yeah.
But a low-frequency survey like LOFAR is like putting on thermal goggles that can see the fading heat of footprints that are hours or days old.
Yes.
You can suddenly see where the wolf was wandering around way in the past, even if the tracks are dried up.
That captures the essence of it beautifully. High frequencies show us the now of the black hole's activity. The low frequency of 144 millihertz allows LOFAR to act as an archaeological tool.
An archaeological tool for space.
It is exquisitely sensitive to that old, dying, low-energy plasma. It allows us to see the ghosts of past eruptions that higher frequency instruments simply cannot perceive.
So just how long has this plasma in the wings been sitting there, fading out? Because we throw around terms like old and ancient in everyday life, but in cosmic terms, what does that actually mean?
It means something vastly different.
How long does it take for the high-frequency glow to completely die off and leave only this 144 millihertz whisper?
We're talking about timescales on the order of tens of millions, sometimes upwards of 100 million years.
100 million years.
The plasma making up those faint wings was violently launched by the supermassive black hole while dinosaurs were still walking around on Earth.
That is insane. So it's literally a fossil.
It is. It has just been sitting out there in the intergalactic void, slowly cooling, slowly expanding, and slowly fading away ever since.
And because LOFAR can finally detect this incredibly ancient plasma, it gives us a window into a history that spans millions of generations of human lifetimes.
It's a deep look back in time purely through the aging of plasma.
Okay, so we have the morphology, the X's and the Z's. We have the data over 1,000 newly found objects. And we know the plasma forming these wings is ancient, revealed by LOFAR's low-frequency time machine.
Right.
But all of that just brings us to the biggest, most complex mystery of this entire discussion. How do these wings physically form in the first place?
That is the big puzzle.
What actual mechanism caused a straight-shooting pair of jets to suddenly grow perpendicular arms or twisted Z-shaped tails?
This is where the detective work really begins.
And astronomers have lined up 4 primary suspects, right, for competing scientific models to explain this morphological mystery. Let's really take our time and dig into the physics of each of these, because it is wild.
It is a phenomenal puzzle. And viewing them as suspects is the right approach. Because right now, astronomers are essentially standing at the scene of a cosmic crime.
Trying to reconstruct an event that happened 50 million years ago.
Yeah.
Based purely on the scattered debris.
Exactly. The reality is there might not be a single culprit. Different theories might explain different shapes. But let's start with the first and perhaps the most dramatic theory: jet reorientation or precession.
Okay, here's where it gets really interesting. Because when you say jet reorientation, you are talking about the central supermassive black hole. This object, weighing billions of times more than our sun, physically changing the direction it is pointing. Why flip the whole black hole?
Exactly. It's called precession. Remember that the jets are strictly launched along the spin axis of the supermassive black hole. They shoot out of the geographic north and south poles of the spinning singularity.
Right.
In this theory, the wings are not some new phenomenon. They are simply the old lobes.
Oh, so they used to be the main jets.
Yes. They were formed millions of years ago when the black hole was pointing in one specific direction. Then, something profound happened to alter the black hole's spin axis. The entire black hole tilted.
And then what?
When it turned back on and resumed feeding, the new jets fired out in a completely new direction, creating the new lobes we see today.
And the old lobes.
The old lobes were left behind in the old orientation to slowly age, cool, and fade into the diffuse wings.
Which perfectly explains the X shape.
It naturally creates that symmetrical X shape with 2 old arms and 2 new arms crossing directly over the central core.
But hold on, how on earth do you tilt a supermassive black hole?
It takes a lot.
It's not a spinning top on a coffee table. It has the mass of 1 billion stars. The amount of kinetic energy required to just casually nudge its axis must be incomprehensible. What could possibly generate that kind of force?
You're right to be skeptical of the energy involved. It requires an incredibly violent, rare event. And the most likely candidate is a major galactic merger.
2 entire galaxies colliding.
Yes. Imagine 2 entire galaxies, each with its own supermassive black hole at the center, colliding and merging over millions of years. Eventually, due to gravitational friction, those 2 black holes will sink to the absolute center of the new combined galaxy.
So they find each other in the middle.
And they form a binary pair spiraling around each other. As they spiral closer and closer together, their immense gravitational fields interact in incredibly complex ways.
I'm guessing this involves Einstein's relativity.
Heavily. Through a process related to general relativity, specifically involving gravitational waves and something called the lens-Thirring effect or frame dragging.
Frame drag, that sounds like sci-fi.
It does, but it's real physics. You see, a spinning black hole doesn't just sit in space. Its immense gravity literally drags the fabric of space-time around with it.
Like a spoon spinning in a jar of thick honey.
That's a perfect analogy. The honey closest to the spoon gets dragged in a circle. Now, when 2 of these spinning space-time whirlpools get close to each other, the torque forces are unimaginable.
The fabric of reality is just twisting.
Exactly. And the spin axis of the primary black hole can be violently flipped or precessed right as the 2 black holes finally merge into a single, more massive singularity.
That is just staggering. The fabric of reality twisting until the black hole flips over. So an X-shaped galaxy might actually be a massive, glowing tombstone marking the exact site where 2 supermassive black holes collided and merged millions of years ago.
That's exactly what it could be.
The X is the literal scar left on the universe by that collision. That's a hell of a theory. Okay, what is suspect number 2?
Suspect 2 is less about violently episodic events like mergers and more about the continuous, ongoing fluid dynamics of the environment. It is called backflow and hydrodynamic deflection.
Hydrodynamic deflection, so fluid mechanics in space.
Right. To understand this, we have to look at what happens when the incredibly fast, tight jet of plasma hits the much denser intergalactic medium at the end of its path.
Right, our cosmic fire hose hitting the invisible wall of the IGM.
Exactly. When the plasma hits that wall, it goes through the terminal shock. The forward momentum is abruptly halted, but the plasma has to go somewhere.
It can't just vanish.
No. So following the laws of fluid dynamics, it splashes outward and then flows backward toward the host galaxy.
It flows back the way it came.
Yes, it essentially envelops the incoming jet in a massive, expanding bubble or cocoon of older, slower plasma. Now, in a perfectly uniform environment, this cocoon would just be a fat, symmetrical oval surrounding the jet.
Like a hot dog bun around a hot dog.
Sure. But the space immediately surrounding a galaxy isn't perfectly uniform.
So what happens when this plasma flows backward toward the center and hits something?
Well, as this highly pressurized plasma flows backward toward the core, it might encounter denser material in the galaxy's own interstellar medium.
Like what?
For instance, many of these host galaxies have a dense, rotating torus or disk of cool gas around their equators.
A big donut of gas.
Right. When the backflowing plasma hits that denser equatorial disk, it can't push through it. The disk is too heavy. So following the path of least resistance, the plasma gets squeezed and squirted outward sideways, perpendicular to the main jets.
Just shooting out the sides.
Over millions of years, this continuous sideways squeezing creates the massive, faint wing structures.
Okay, I think I have an analogy for this one.
Let's hear it.
Imagine you turn on the faucet in your kitchen sink, and the water is running perfectly straight down. That stream is your jet. But then you hold a large spoon right under the stream. The water hits the spoon, that's the terminal shock, and splashes back up. But as it splashes back up and hits your hand holding the spoon, it can't go any further, so it squirts out sideways in these 2 wide, flat fans of water.
That's actually a great way to think about it.
So in this scenario, the black hole is the faucet, the terminal shock is the spoon, and the backflow hitting the dense galactic gas is what forces the plasma to fan out sideways into wings.
It's a very practical way to visualize the mechanics. And notice that it relies purely on hydrodynamics, the physics of fluids in motion reacting to the pressure gradients of the surrounding space.
So the black hole doesn't have to flip or merge or do anything crazy.
No, it doesn't require the black hole to ever change its spin or undergo a massive merger. It is a continuous, passive process dictated entirely by the shape of the gas in the host galaxy.
All right, so theory 1 is a violent axis flip from a merger. Theory 2 is fluid backflow squirting sideways against a dense galactic disk. That brings us to theory 3, environmental interactions. How is this different from the backflow hitting the galactic gas we just talked about?
Well, theory 3 moves the focus entirely outside the host galaxy and looks at the vast intergalactic environment on a much larger scale.
Way out in deep space.
Right. It proposes that the jets are plowing into what astronomers call an anisotropic medium.
Anisotropic, meaning not the same everywhere.
Exactly. Anisotropic simply means that the properties of the environment are not the same in all directions. Out in deep space, galaxies are not just floating in a perfectly empty, uniform void.
They hit the cosmic web.
They are embedded in it. Vast, invisible filaments of dark matter and intergalactic gas. If a radio galaxy happens to be sitting near one of these massive filaments, or perhaps near the dense edge of a galaxy cluster, the environment the jets are shooting into will be physically denser on one side than the other.
So the jets are essentially driving into a cosmic crosswind, or hitting uneven terrain.
You could certainly think of it as uneven terrain. As the jets, or the expanding lobes, expand into this environment, they experience immense pressure variations.
Ram pressure.
Ram pressure or buoyancy effects, yes. The plasma will naturally expand faster and further into the less dense, emptier regions of space, and it will be physically blocked or pushed away by the denser regions.
Oh, like inflating a long balloon inside a small, irregularly shaped box. The balloon is going to deform and bend to fill whatever available space there is?
Exactly. In this scenario, the wings are just the plasma being physically deflected or squeezed out into the path of least resistance by the invisible terrain of the cosmic web.
And this one makes a lot of sense for the Z-shaped galaxies.
Right, it does.
Because if a jet is shooting out straight and it hits a dense, invisible wall of intergalactic gas on its left side, it's going to get deflected to the right, creating that bent Z-like arm at the outer edge.
Right, like a fast-moving river hitting a massive bedrock formation and being forced to take a sharp, unexpected turn.
The morphology points directly to the cause.
If you see a Z-shape with those bent-off wings at the extreme edges of the lobes, you are highly likely looking at an environmental deflection. The surrounding intergalactic environment is literally bending the galaxy out of shape.
Okay, that leaves us with theory 4. The intermittent or restarted activity model. This one involves what the researchers call double-double galaxies.
Yeah.
What does that mean for a supermassive black hole?
It means the central engine is sputtering.
Sputtering.
Yeah. It is not a continuous, steady fire hose that stays on for hundreds of millions of years. It is highly episodic. The black hole goes through a period of intense feeding, launching a massive pair of jets that travel out millions of light years and form enormous primary lobes.
Okay, standard so far.
But then, for whatever reason, maybe it temporarily runs out of easily accessible gas. The feeding stops.
The black hole goes on a diet.
The black hole goes completely dormant. The jets turn off. Those massive lobes are left out there in the void to slowly age, expand, and fade. Millions of years pass in silence.
Just waiting.
Then, a new cloud of gas falls into the center, the accretion disk reignites, the black hole wakes up, and it fires a new pair of jets.
So you end up with a new, younger pair of jets shooting out inside the hollowed-out channel left by the old jets.
Exactly. You get two distinct sets of lobes, a double-double.
Double-double, got it.
Now, if those new jets are even slightly misaligned from the original axis, or if the old plasma has expanded and drifted during the tens of millions of years of downtime.
Oh, I see where this is going.
The interaction between the fast, powerful new jets and the old, fading plasma can create the appearance of wings.
Because the new jets crash into the old debris.
Right. The new jets might punch through the side of the old cocoon in a way that pushes the old plasma outward, creating those perpendicular structures.
It is so fascinating because looking at these 4 suspects, spin flip, backflow, environmental deflection, and intermittent restarting, it seems like they might all be true to some extent, just for different galaxies.
They very well might be.
You mentioned earlier that we have these distinct X and Z shapes. Do the researchers think the specific shapes align with specific theories?
That is exactly where the detailed analysis is heading, because the X-shaped galaxies, the XRGs, have such beautifully symmetric wings emerging right from the central core.
They lean to the internal mechanisms.
Strongly lean toward them. Theories like the black hole spin flip from a violent merger, or the backflow hitting a dense symmetrical central disk, perfectly explain that symmetrical centrally located X.
And the Z-shapes.
On the other hand, the Z-shaped galaxies, the ZRGs, with their offset bent wings at the outer edges, almost certainly lean toward Theory 3. Environmental deflections at the edges of the lobes physically pushing the plasma around.
So different shapes literally point to different histories.
Exactly.
We have spent a lot of time looking right at the black holes, the jets, and the plasma physics. But what kind of house do these monsters actually live in?
The host galaxies.
Yeah, because someone listening might be thinking, okay, giant glowing X's in space are cool, but why does this matter for the rest of the universe? Why should anyone besides a dedicated radio astronomer care about these structures?
That's a fair question.
And I think to answer that, we have to look at the host galaxies themselves and this concept that astrophysicists call the universal thermostat.
Yes. This is where we bridge the gap between exotic, large-scale astrophysics and the fundamental evolution of the universe we live in.
So what did they find when they looked at the hosts?
When astronomers looked at the optical and infrared data to see what kind of galaxies host these massive winged structures, they found they are predominantly hosted in massive elliptical galaxies.
Now, for anyone who might not be totally caught up on galaxy taxonomy, an elliptical galaxy isn't like our Milky Way, right?
Well, not at all.
The Milky Way is a spiral galaxy. It has those beautiful sweeping arms full of blue, newly forming stars. An elliptical is a totally different beast.
Very different. An elliptical galaxy looks more like a giant, featureless, glowing football or sphere.
Just a big blob of stars.
In astronomical circles, they are often colloquially called red and dead galaxies.
Red and dead. Sounds bleak.
It's descriptive. They are red because they are full of old, cool, red-burning stars, and they are dead because they have almost completely stopped forming new stars.
So they aren't making baby stars anymore.
No, they lack the vast clouds of cold, dense molecular gas needed to birth stellar nurseries, and they are absolutely massive. They are often the largest individual galaxies in the entire universe, sitting heavily at the very centers of huge galaxy clusters.
But wait, if they're so massive and they have so much gravity, shouldn't they be pulling in huge amounts of intergalactic gas from the cluster around them?
You'd think so, yes.
And if they pull in gas, that gas should cool down, clump together, and form billions of new stars. Why are they dead? I know this was something that baffled astronomers for a long time, the cooling flow problem.
Exactly, the cooling flow problem.
The math said these galaxies should be churning out new stars infinitely, growing bigger and bigger until they consume everything around them. But when we actually look at them, they are just sitting there completely dormant.
You have hit on one of the most important unresolved problems in modern cosmology over the last few decades. The theoretical models predicted that the hot gas surrounding these massive ellipticals should cool and collapse inward, creating a runaway starburst.
But it doesn't.
Observational data consistently showed that wasn't happening. Something was actively stopping the gas from cooling. Something was regulating the growth of the galaxy.
And let me guess, that something is the supermassive black hole at the center.
Acting through a process we call active galactic nucleus, or AGN feedback.
AGN feedback. Okay, let's break that down because it sounds like a crucial mechanism. Active galactic nucleus just means a black hole that is currently eating and shooting out jets.
Right.
So how does a black hole provide feedback to stop an entire galaxy from forming stars?
Think of the black hole as the thermostat for the entire galaxy. And the surrounding intergalactic gas is the ambient temperature of the house.
Okay, I'm with you.
When the gas around the galaxy begins to slowly cool down, it loses pressure and starts to fall inward toward the center. It wants to condense. It wants to form stars.
But it doesn't get the chance.
Because some of that cooling gas inevitably falls all the way down into the central supermassive black hole's accretion disk.
The black hole finally gets its meal.
Exactly. And when it feeds, it ignites. It launches those colossal relativistic jets we have been talking about.
The fire hoses.
Those jets, carrying absolutely unimaginable amounts of kinetic energy smash into the cooling gas that is trying to fall in. They act like giant cosmic heating elements.
Oh, this physically heats the gas back up.
The shock waves and the intense radiation physically heat the gas back up, blowing it outward and completely preventing it from condensing into stars.
So the gas tries to cool, the black hole eats a tiny bit of it, turns on the massive heater, and blasts all the gas away, stopping star formation entirely.
That's the feedback loop.
But then what? If it blows all the fuel away, it stars itself.
It does.
Right.
The jets violently blow the fuel away, the black hole starves, and the jets turn off. The heating stops.
And then the cycle repeats.
Millions of years pass in quiet dormancy. The gas slowly cools down again, begins to fall inward again, and the cycle repeats. This self-regulating cycle, the thermostat turning on and off over cosmic time, is AGN feedback.
That is incredible.
It is the fundamental reason why galaxies do not just grow infinitely massive. It is why the universe looks the way it does today. Without supermassive black holes choking off star formation with these massive jets, the entire structure of the cosmos would be radically unimaginably different.
If we connect this to the bigger picture, then these winged radio galaxies we were talking about, these massive X and Z shapes, they aren't just arbitrary oddities. They are essentially a temporal record.
They are.
They are a fossilized history of this exact thermostat mechanism at work over hundreds of millions of years.
That is precisely why this new catalog of over 1,000 winged galaxies is so invaluable to cosmologists. Because we are seeing different stages of this crucial cycle.
Like freeze frames of a movie.
When we look at an X-shaped galaxy, if the spin flip theory is correct, we are looking at a black hole that merged, violently flipped its axis, and started heating a completely different region of the surrounding space.
Heating the house from a different corner.
Exactly. And if the intermittent model is correct, we are literally seeing the physical evidence of the thermostat turning off for tens of millions of years, leaving the old lobes behind, and then violently turning back on to create new jets.
Leaving it double-double.
These wings are the physical evidence, the ancient receipts, proving exactly how these black holes switch on and off and redirect their massive energy output to regulate their host galaxies.
It is incredible. We are basically reading the long-term climate history of a galaxy by looking at the shapes its black hole left behind in the plasma.
It's cosmic paleontology.
But believe it or not, the scale gets even bigger. Because we have zoomed from the black hole out to the jets, out to the host galaxy, and now we need to zoom out to the largest scale possible in the entire universe.
The cosmic web.
We touched on this briefly with the environmental deflection theory, but these winged galaxies are actually being used as tools to map structures that are otherwise completely invisible to us. They act as cosmic weather vanes.
Yes, and this is where the implications for cosmology become truly profound. We mentioned the cosmic web earlier.
Right.
To visualize it, imagine the universe not as a random scattering of galaxies, but as an immense three-dimensional spider web. The threads of the web are colossal filaments made primarily of dark matter, stretching for hundreds of millions of light years across the void.
Yeah, where the threads cross.
Where these dense filaments intersect, you have nodes, and that is where massive galaxy clusters form. And in between the filaments, you have massive empty voids.
So the galaxies are just like water droplets clinging to the threads of this invisible dark matter web. But there is also regular matter gas strung out along those filaments, right? It isn't just dark matter.
There is regular matter, and it is a massive component of the universe called the warm-hot intergalactic medium, or WIMM.
What?
It is a highly ionized, very diffuse plasma that makes up a significant portion of the normal baryonic matter in the universe. The problem is, because it is so incredibly diffuse and so hot, it is almost impossible to detect directly with standard optical or even traditional X-ray telescopes.
We just can't see it.
For decades, astronomers struggled with the missing baryon problem. We knew from our math of the Big Bang that there should be more normal matter out there, but we simply couldn't see it.
It was hiding.
We theorized it had to be hiding in these cosmic web filaments.
Which brings us right back to our giant glowing Z-shapes.
Yeah.
If we can't see the cosmic web, but we can see these massive, faint wings of plasma interacting with it. Are we basically using the belches of supermassive black holes to map the invisible skeleton of the universe?
You know, that is an incredibly vivid way to put it, and it is entirely accurate. Think of those millions of light years long jets and wings as giant cosmic windsocks.
Like at an airport.
Exactly. You know those bright orange fabric cones you see at an airport?
Mm-hmm.
By themselves, they don't do much, but when the wind blows, they fill and point. instantly telling you the direction and strength of an invisible force.
The plasma is the fabric.
The diffuse plasma in these radio galaxy wings is so incredibly light and sensitive that it gets physically pushed around by the slightest density gradients and intergalactic breezes within the GWIM.
So when astronomers look at a Z-shaped galaxy, and they see exactly how much the wing is deflected and at what angle, they can run the math backward.
Run the simulation in reverse.
And calculate the exact density of the invisible dark matter filament and the whim that pushed it out of shape. We are seeing the invisible wall by looking at how the plasma splatters against it.
That's the principle entirely, and it isn't just about tracing the density of the gas. The deflection of these wings also traces the intergalactic magnetic fields.
The magnetic fields are out there too.
Space is threaded with incredibly weak but immensely large magnetic fields that follow the cosmic web. As the synchrotron-emitting plasma in the wings interacts with these external fields, it leaves a signature.
How do they read the signature?
By studying the polarization of the radio waves coming from the wings, essentially looking at the orientation of the light waves themselves, astronomers can begin to map the magnetic topography of the cosmic web.
Map the magnets of the universe.
This is an entirely new frontier in cosmology, made possible purely because we now have a statistically large enough sample of these windsocks pointing in all different directions across the sky.
It just highlights how perfectly interconnected everything is. The spin of a black hole, an object no bigger than our solar system, can launch a jet that creates a wing 1 million light years wide, which then bends in a way that allows a human on Earth to map the dark matter structure of the universe itself.
It's a beautiful chain of causality.
It's breathtaking. But where do we go from here? The LOFAR survey found over 1,000 of these, but you mentioned LOFAR is essentially an ongoing project.
Yeah.
What is the road ahead for this specific field of research?
Well, the current catalog is really just the opening chapter of a much longer book. First, there is the immediate, grueling follow-up work on these 1,000 newly found objects.
You have to actually study them now.
Right. Astronomers will need to perform much deeper optical spectroscopy on the host galaxies to accurately determine their masses, their stellar ages, and their exact distances.
The nitty-gritty details.
They need those deep polarization studies we just talked about to map the magnetic fields inside the wings. And perhaps most importantly, theoreticians are running incredibly complex, supercomputer-driven hydrodynamic simulations.
Trying to build them in a computer.
Trying to recreate these exact X and Z shapes in a virtual sandbox. By tweaking the parameters, simulating a spin flip, or simulating a cosmic crosswind, they can see which mathematical model perfectly matches the observed reality.
And beyond just studying the ones we have, we are inevitably going to find more, right? Because the instruments are only getting better.
Exponentially better. LOFAR itself is currently undergoing a massive hardware and software upgrade to LOFAR 2.0.
Upgrading the math.
And the hardware, which will dramatically increase its sensitivity and its resolution. Furthermore, researchers are now applying advanced machine learning techniques, artificial intelligence, to scour even larger upcoming data sets.
Oh, having AI look for the faint shapes instead of humans.
Exactly. Human eyes are great, but AI can be trained to spot the incredibly faint, diffuse signatures of winged galaxies in fractions of a second without fatigue.
That's going to speed things up.
But the real monumental game changer on the horizon is the SKA, the Square Kilometer Array.
The SKA. That is the massive radio telescope project being built across multiple continents, right?
Yes, across vast tracts of Africa and Australia. When the SKA comes fully online, it will be the largest and most sensitive radio telescope ever constructed by humanity.
It's going to dwarf everything.
It will make LOFAR look like a pair of opera glasses. If LOFAR found 1,000 of these winged galaxies, the SKA is expected to uncover tens of thousands, perhaps hundreds of thousands of them.
Hundreds of thousands.
Looking all the way back to the dawn of the universe, it will completely revolutionize our understanding of how supermassive black holes and galaxies have co-evolved since the Big Bang.
So what does this all mean? When we take a step back from the megahertz and the plasma physics and the fluid dynamics,
Right.
What is the core takeaway for you listening to this?
It's a profound shift in perspective.
I think the fundamental truth this discovery underscores is that the universe is not static. When we look up at the night sky, it feels permanent, it feels quiet.
It's deceivingly quiet.
Even when astronomers looked at traditional straight-line radio lobes in the past, they seemed like these stable, fixed structures. But what this new low-frequency data reveals is that those supposedly quiet objects are actually intricate, layered histories of unimaginable violence, profound renewal, and constant interaction.
They're living histories.
Supermassive black holes are not just destruction engines. They're the ultimate sculptors. They dictate the size of galaxies, they regulate the birth of stars, and they leave behind these beautiful, million light-year wide X and Z monuments, glowing faintly in the radio dark, chronicling their restless ancient activity.
This really reinforces a vital lesson for science. There is always more hiding just out of sight.
We just have to know how to look.
Right. While a catalog of 1,000 winged galaxies is a monumental achievement, it really just proves how much we were missing when we only looked with high-frequency tools.
We were blinding ourselves.
Every time we build a new instrument that looks at the universe in a slightly different way, whether it is a different frequency, a higher sensitivity, or a wider field of view, we uncover entire populations of objects that fundamentally rewrite the textbooks.
It's a never-ending process of discovery.
These newly found cosmic oddities are the vanguard of a whole new era in extragalactic astronomy. This raises an important question, and it reminds us to constantly question our assumptions, because the universe is far more dynamic, morphologically rich, and deeply interconnected than we ever previously imagined.
Which leaves me with one final kind of haunting thought.
Let's hear it.
We have been talking about these massive ellipticals, millions of light years away, out in the deep cosmic web, but we have a supermassive black hole, too.
We do. Sagittarius A.
Right in the center of our own Milky Way galaxy.
Yeah.
And right now, it is quiet. It is a sleeping giant, just passively snacking on little wisps of gas. It doesn't have towering radio jets.
Not currently, no.
But if these massive winged structures we've talked about represent distinct ancient epochs of black hole activity separated by tens of millions of years of dormancy, what exactly triggers a sleeping monster to suddenly wake up, shift its axis, and begin carving new shapes across the cosmos?
It's a sobering question.
Could our own sleeping giant ever wake up from its slumber? And if it did, millions of years from now, could an alien astronomer in a distant galaxy point their low-frequency telescope at the Milky Way only to see a colossal, glowing Radio X painted violently across our sky?
It's entirely possible.
Something to think about the next time you look up at the dark.